In this slidecast, we'll talk about heaps and priority queues. A heap is a complete binary tree. The values of each node is greater than or equal to all values in the node's subtrees. So notice in this tree, 89 is the largest value in the tree. In this subtree located here, 32 is the largest value in this subtree. Now the heap shown below is called a min heap because the root node stores the smallest value. It's also possible to build and use a max heap, which each node's value is larger than or equal to the value of its children, and the root node stores the largest value. The text has algorithms and illustrations for max heaps, so we'll present the corresponding algorithms and illustrations for min heaps here in this slidecast. So you'll have examples of both types available to you. A heap is a complete tree with the following properties. The value in the root is less than or equal to all items in the tree, and every subtree is a heap. Okay, so this is the min heap. Now, the algorithm for inserting into the heap. We first insert the new item in the next position at the bottom of the heap. So here, 89, we'll place 89 at the next available location at the bottom of the heap. And while the new item is not at the root, and the new item is smaller than its parent, then we'll swap the new item with its parent, moving the new item up the heap. Now in this case, 89 is greater than its parent, so it stays in that location. Suppose we next added an 8 to the heap. Now since 8 is less than 66, we'll swap it with its parent. Since 8 is less than 29, we'll swap it with 29. And now 8 is in its proper location, and we have a valid heap. Now the algorithm to remove from a heap. We remove the item in the root by replacing it with the last item in the heap. So one idea here is that when we remove an item from the heap, we're always going to remove the smallest item. Here we're not talking about just removing an arbitrary item. And then while this item has children and the item, the last item in the heap is larger than either of its children, we swap that item with its smaller child, moving LIH down the heap. So the idea here is if we want to remove something from this heap, we'll remove the 6 and we'll replace the 66 at the top. And then while it's larger than either of its children, we want to swap it with the smaller child. So we'll swap 66 with 8. And now 66, its smallest child is the 29. And then it has no more children, and so we're finished. And now you'll see that what's left is a valid heap. Now, because a heap is a complete binary tree, it can be implemented efficiently. Because a heap is a complete binary tree, it can be implemented efficiently using an array rather than a linked data structure. If we have the following min heap, if we have this array, we can lay out the values of the heap in the following fashion. We can put the root in the first location. The 2 nodes at the next level occupy the next 2 locations. The 4 nodes at the third level occupy the next 4. And then the nodes at the last level fill the next slot. Now, for a node at position P, its left child position starts at 2P plus 1, and the right child starts at 2P plus 2. Notice for here, we have 18 starts at a location P1, and its left child starts at the location 2P plus 1 and 2P plus 2. So 2 times P, 2 times 1 is 2 plus 1 is 3, and 2 times 1 is 2 plus 2 is 4. And this relationship holds for all parents and children in this heap. So here's 20 and its children, 37 and 26, and so forth. Now a node at position C can find its parent at C minus 1 divided by 2. Now if we want to insert into a min heap that's implemented as a vector, we can start by inserting the new element at the end of the vector, and we could set child equal to table size. Okay, I think that should be table size and not table size minus 1. Since there are 13 items in the heap, we set child to be 13 and we insert 8 at location 13, assuming zero-based indexing. Next, we set the parent to child minus 1 divided by 2. So the parent's at location 6 that has a value of 66. And while the parent's greater than 0 and the parent value is greater than the child value, then we want to swap the parent and the child. So we'll swap 8 with 66. Then we set child to be equal to the parent, and we compute a new parent. And we continue while the parent's greater than 0, and once again, the parent value is greater than the child value. We'll go ahead and swap those. We reset child equal to parent, and we calculate a new parent. And in this case, child is greater than parent, so we're finished. And now we've adjusted that so that 8 is in its proper position in a valid heap. Now removal from a min heap that's implemented as a vector, here's some pseudocode for this. We start by removing the last element, and then we set the item at 0 to this value. So we set parent to 0, and while true, we set the left child to 2 times the parent plus 1, and the right child to left child plus 1. And if the left child is greater than or equal to the table size, we break out of the loop. Otherwise, we assume that the min child, the smaller child, is the left child. And if the right child is less than table size and the left child is greater than the right child, then we set min child to the right child. And if the parent is greater than the min child, then we swap the parent with a min child and we set parent to min child. Otherwise, we break out of the loop. Now, the removal algorithm traces a path from the root to a leaf, and the insertion algorithm traces a path from the leaf to the root. So we'll have at most h steps, where h is the height of the tree, and the largest full tree of height h has 2 to the h minus 1 nodes. So the smallest complete tree of height h has 2 to the h minus 1 nodes. Both insert and remove are order log n, where n is the number of items in the heap. Now the heap is used to implement a special kind of queue called a priority queue, and sometimes a FIFO queue may not be the best way to implement a waiting line. A priority queue is a data structure in which only the highest priority item is accessible. For instance, in a print queue, sometimes it's more appropriate to print a short document that arrived after a very long document. And a priority queue is a data structure in which only the highest priority item is acceptable, as opposed to the first item that was entered. So here's a queue, a print queue. We've got a 1-page job and a 4-page job. And then after we insert a document with 3 pages, here's our priority queue. And then after inserting a document with 1 page, if this receipt comes along, we'll go ahead and give that a priority to print before these longer jobs. C++ has a priority queue class. It uses the same interface as the queue in Chapter 6. And the differences are in the specification for the top and pop functions. These are defined to return a largest item in the queue rather than an oldest item. In a priority queue, just like a heap, the largest item always is removed first. And because heap insertion and removal is log n, a heap can be the basis of a very efficient implementation of a priority queue. So the author's priority queue, he's placed it in a different namespace to be distinct from the standard library's priority queue, which also uses the heap as the basis of its implementation. The interfaces for our class and the standard class are identical, but the implementations are slightly different. To remove an item from the priority queue, we take the first item from the vector. This is the largest item in the max heap. And then we remove the last item from the vector and put it into the first position, overriding the value that's there. And then following the algorithm for a max heap, we move this item down until it is larger than its children or it has no children. So the priority queue has a container for the data. It's a sequential container to hold the data, and a standard vector is used by default, but a dec might also be used. And comp is a function object that performs the comparison, and by default this function is equivalent to the less than operator. And this is a less than operator that takes 2 parameters, so this is a non-member function for this less than operator. And there's code for the priority queue in your book, and I encourage you to go look at it and make sure you understand all the lines for it. Specifying the defaults for a template class. Here's a priority queue class that's a template class, and it prescribes defaults for the data types, container, its default is a vector, and compare, which is default is the operator less. And in an application, the declaration of a priority queue in this fashion creates a priority queue that uses a vector for the storage of string data and an operator less for comparisons. Here's a declaration that creates a priority queue, PQB. It uses a dec for storage of string data and operator less, the default for comparisons. There's code in your book for a push function and for a pop function. And when comparing elements in a priority queue, we usually insert objects that implement the less than operator and use their natural ordering. However, we may want to specify a different ordering from that defined by the object's less than operator. For instance, files to be printed might be ordered by their name using the less than operator function, but we may want to assign priority based on their length. So to indicate that we want to use an ordering that's different from the natural ordering for the objects in a heap, we provide a template argument that is a function class. And this function class's operator performs the comparison. So the class print document is used to define documents to be printed. That class implements the less than operator, but its operator function performs a lexical comparison of document names, and we want to print them according to the file size. So the class has a getSize function that gives a number of bytes to be transmitted to the printer, and a getTimestamp that gets the time that the print job was submitted. So by using a priority value that's a combination of size and time, we achieve a balanced usage of the printer. And here's the class definition for compare print documents. And it overrides the function operator, and it returns an order value, a Boolean result of the order value of the left if it's greater than the order value on the right. On the client program, we use the following definition for a print queue. And if a compare function class isn't provided when the priority queue is declared, then the standard less than class is used. And this template class is defined in the header, functional, and it has a definition that's equivalent to the following. So we have less, which is a template class. It has a Boolean operator that takes 2 constant references, left and right. And it returns a result of left if left is less than right. And that brings us to the end of this slidecast.